Today we are going to discuss magnetics, that is uh, slightly more complicated than electrostatics. So here the content that I'm going to discuss today will be very similar to the physics 2041. So if you can review this chapter 10 and 11 of Physics 2041, that might give you some reminder about the magnetostatistics that I'm going to talk about today. So this chapter and the chapter following which is about the magnetic fields with matter, they are very similar to the previous chapters on electrostatistics. So here, if you look at the Maxwell's equations for all the static problems, the time-dependent fields here are gone. So the del cross E equal to 0, and likewise in this magnetostatistics, the B field here, because there is no time dependence on the E field, so on the right hand side is also simplified. And now if you compare these two terms, uh, both of these equations shares equation that's 0, and now in this electric static problem, we have this source term that is rho over epsilon naught, and in this magnetostatic problem, we have this mu naught times J. This J is a current and is also a source in this problem. So now, last time we also, in the very beginning of the lecture, we also told that the Lorentz force is responsible to calculate the force produced by the field. And we are very familiar that the E field, the force that is due to the E field is Q times E, and the full expression for the Lorentz force is uh, Q times E plus V cross B. And so here, because this is the electric force, this is the magnetic force. And so the magnetic force is a cross product of this V and the B. So the V is the velocity of a charged particle, and the B is the magnetic field. So here, because here this V is a charged particle, and a current can actually be think of a moving charge. So whenever you have a moving charge, you have a current. But just keep in mind that a moving charge is not simply a current, but if you have a point charge that moves, and it's slightly different from a current in the sense that it's no longer a static problem. So in order to have a static problem here, not only this charge should move there, if a charge has a velocity that moves, you have to also have like charge following itself, a different point charge that following this point charge to fill out the blanks that it makes once it moves. So in static problem, you have to have at least a line charge, and that this entire line charge moves forward. And in this case, you can form a current. So typically, in magnetic static problems, we have currents, and the currents we will see later that they are typically closed loop, because you cannot have like typically if you don't have a source that generates this currents, then they form a loop. So so here for the for the charge to describe the interaction between a charge and another charge, well, as we suggested that what we do is we consider an E field. So a charge can produce an E field, and then according to the Maxwell's equations, and then this E field will apply a force according to the Lorentz force law. And likewise, here the current can also produce a B field according to the Maxwell's equation, and the B field will also act a force, and this force will be acting on this current, and then this describes the interaction between a current and another current. And this here, this step is described by the Lorentz force law. So, for example, for a line current that's running upwards, we can it produce a magnetic field that circles this current, and you can determine the direction by using the right-hand rule. So, if you still remember, the magnetic field strength is inversely proportional to this radius to this current. And now this, suppose that you have two currents running parallel to each other, and then because of this magnetic field, it produces the Lorentz force. So if you to calculate the direction of the force, you also need to use the right-hand rule. So it's V cross B. So remember that in the very first of the lecture, I suggest to use the right hand. And so here the V is pointing upwards. So if could you check my hands here? Like, so here the V is pointing upwards, and then there is a you rotate your hands from the upward direction of the V to the direction that's parallel to the B direction. Then that determines the F force. I don't know if it's exactly the same direction to your screen. But from that, you can determine that the force is actually pointing towards the wire 1. So in this case, the two parallel running wires with the same current direction will be attracted to each other. So for this problem, you can also try to change the current direction. Say that if you have one of the wire have current coming up and another is having a current going down, then the force should be a repulsive force, and that's because the V flips the sign, which flips the sign of the F. Okay, from this Lorentz force law, we can actually already obtain quite a few things. So let's take a look at some of the examples. Here, the first example I want to mention is the cyclotron motion. So, for example, here, if we look at the previous slides, so F is equals V cross B, also times the Q. And that means that the force will always be perpendicular to this velocity V. So if this means that the magnetic force can actually provide a centripetal force. Here the centripetal force is something real, so instead of a centrifugal force, which is something imaginary. So this centripetal force will make the particles form a circular trajectory. So if the velocity of the particle is a constant, so now this is simply this simple cyclotron orbitals that I guess you are already very familiar. So here I try to remind you. So if you can get this radius of this cyclotron orbital by checking its force. So the the Lorentz force is BV cross Q. So if the magnetic field is perpendicular to the plane of this orbital, then the B is a constant, and the B cross V is also a constant in magnitude, but changing direction. And this force should be equal to this MA, which is the centrifugal force. And if you still remember your physics course, that should be mv squared divided by r. And if you don't remember, I guess you can also derive it from this MA, and the A is related to this change of velocity. So A is V dot, and I guess V is related, so this V dot is dV dt. The dV here is the it is let me see. The dV should be related to this angular frequency, and guess it should be omega r dt, and since this omega is a constant, so dr dt equals to v, and the omega equals to v divided by r. So that gives you mv squared over r. And now if you combine these two equations, you can determine the radius of this cyclotron motion. And you can see that this radius is actually proportional to this m times v, and which gives the momentum. So it actually is a standard means to measure the momentum of a charged particle. So as long as you know your magnetic field and the charge of this particle, and if you determine the radius of this cycle orbitals, and then you can actually determine your momentum of this charged particle. And another thing that I want to mention is that if you calculate the angular frequency, the angular frequency is v over r, and it's actually something independent of the velocity of the particle. So no matter how fast your charged particle is moving in the magnetic field, the time it takes to finish a cycle is exactly the same. So that's the reason you can build a cyclotron accelerator like this. So in this accelerator, I think you have seen it in the Physics 2041 course. So I just briefly mentioned that. Say that if you in the middle, it's an electric field, and you can charge your particles. You can accelerate the particles here from one end to the other end, and now it will finish one cycle here, and once it's finished the cycle, you can flip your sign of the electric field, and it will continue to be charged here, to be accelerated here, and then because the speed increases, it will finish a larger circle. And at that exact moment, because the frequency is the same, and that means that the time it takes to finish half cycle is exactly identical. So as long as you alternate your E fields in a exact same frequency, then you will always be accelerating your charged particle, and as you go round and round, the particle will be charged to a larger and larger speed. and as your radius goes larger, according to the equation here, because r is larger, the momentum you get from your charged particle is also larger. And then in the end, as it exits the channel here, it will reach your targeted speed, and it can be used for high energy physics.
Can I ask a question?
Yeah.
In the Lorentz force, we have F, V, and B as vectors. Why is B the one the pseudo vector instead of the other two?
Can you say that again? You mean in this force?
In Lorentz force, we when we consider the magnetic force, we have three vectors: for F, velocity, and B field. But how do we know that B is the pseudo vector instead of the other two?
I think that's you mean you are saying that here the B field is a pseudo vector, and velocity and the other are not pseudo vectors. So that's, I guess, is because of the definition of the pseudo vector. I don't remember exactly, but I think the vector should be remain the same if you flip, if you do a mirror image and flip, but for the B field, it will change a sign. So for any vector that remains the same after you do a mirror image and flip, then that's a vector. But if a vector changes a sign, then it's a pseudo vector. So it's simply some mathematical definition. So here, I think you don't need to worry about the pseudo vector. So yes, in principle, B field is actually slightly different from the E field. Okay, any other questions? Okay, so let's try to take another example. So say that in the previous example, the B field is perpendicular to the plane of motion, so it's perpendicular to V. And now think that the B field is actually not perpendicular to V, so which means that there is a parallel V that is in the direction of this magnetic field. And in this case, because the because imagine that the force V, the force is QV cross B, and so here this parallel V doesn't contribute to the force at all, and likewise this in this parallel direction, the motion won't be changed as well. And in this case, you simply have a cyclotron orbit plus additional motion along the motion of your parallel velocity, so along the line of this B field. So it will be like something like a spring. Can you speak louder?
In this picture, do you mean that V is the current that flows in this direction? Or in that?
Are you talking about current? Are you talking about current? I didn't hear clearly.
Oh, so is that V
Yes. So
So it is moving in this direction.
depending on the velocity of this charged particle. So if the charged particle have a parallel velocity that's going up, then eventually this will follow an orbital like this. But if the v parallel is going downwards, then this particle will will follow a trajectory like this. So it completely depends on the initial condition or the v parallel. So in another way of saying is that the motion that's parallel to the B field is determined by the particle alone. It is not affected by the magnetic field.
That's why home is just keep in this direction moving instead.
Okay, so the reason that it will make a circle like this because there are also velocity that's perpendicular to the b. So if the particle is moving this, if the particle only have a velocity like this, then it will move like a straight line. But if there are any velocity that's along the perpendicular direction, then it will form a closed loop in the perpendicular direction. Meanwhile, in the parallel direction, it follows a straight line. So if you combine these two motions, it will be a spring-like motion. Okay, so let's take another example. So in the previous examples, I only talk about the effect of magnetic field alone, and now in this example, we both have an electric field and a magnetic field. So the full form of this the full form of the Lorentz force is equal to Q E plus V cross B. So remember that here is V cross B instead of B cross V. So in case that you only remember QVB but don't know the exact sign, you might get, and if you think it's the V cross B is actually different from this B cross V. So you have to remember this sign correctly. Otherwise, you might be mistaken by a -1 factor. So in this example, consider that let's try to imagine what a particle will do under both electric field and B field that's perpendicular to each other. Say that initially the particle is staying at rest here, and you can imagine that B field won't do anything to a particle that's staying still, because for 0V, this term is simply 0. And but it will feel the force of the electric field. So you can imagine that it will go up, and now once it goes up, you can see that it pick up a velocity, and it will feel this magnetic force. So it will deflect the orbital to the direction of, you can determine the direction, right? So it's V, so the V is upwards, and the B is out of the screen, so it should be to the right. So because it feels a force to the right, it will deflect the orbital to moving to the right, right? And now as it continues to move right, it will reach a critical point where the velocity actually being being perpendicular to this E field. So at that point, then all the velocities going upwards are actually transferred to the y direction to the right. So at that moment, then you can imagine that it might be even possible to going backwards because it has some sort of initial velocity, and however, as you continues to go backwards, the E field will let me see. The E field will try to prevent the going going backwards, so it will slow down the particle. So until at some point it becomes stopped, and you can actually sort of imagine that at the path here should be actually similar to the path here, because you can think of some kind of time reversal motion. So as it goes up to the maximum point here, and the motion it follows here can be think of copy of this motion over here, and but instead of reaching from 0 to Vmax, it goes from Vmax back to 0. So somewhat we would imagine that the orbital of the motion of a particle that stands still here will goes to the right here, stops, and then goes to the right and stops, goes to the right, and so it's some kind of skipping stones that's moving actually to the y direction, which is perpendicular to both E and B. So